And the first speaker is Amine Cassimi from CIMAP at the Université de Caen in France. And he will be speaking about site-sensitive processes in dimer collisions from Coulomb explosion to interatomic Coulombic decay.
Thank you, Mr. Chairman. Good afternoon to everyone. As usual, in life, you have two ways of looking to the events happening to you. You have the positive way and the negative way. And for example, being a speaker of the last session of the last day of a conference, you might think that everybody is gone already and you think nobody will listen to your talk. So thank you very much for being here. But there is a positive way to look at this event is also that you can use the slide of all the previous users to make your own talk. So that's what I did. So I think you remember this plenary lecture given by Serge Haroche. And among the interesting things he talked about, he presented this slide where he was talking about quantum simulation with cold atoms. And if we zoom on this part here, we see that by using optical lattices, you can keep atoms together, and you can simulate the matter either in 1D, 2D, or 3D, and to see if you could learn new things concerning solid state or an assembly of atoms with no interaction between them. So in rare gas clusters, the van der Waals forces, which are weak, keep the atoms for you together. And if you are concerned by dimers, this is a 1D simulation of molecules without any covalent interaction between the atoms. And if you choose correctly the atom, you can change the distance between the atoms from a short distance for helium to a large distance for xenon. However, you should be careful and do not forget that even if the potential is very narrow, the nuclear wave function can be very wide, and you might be surprised if you compare these wave functions to other nano objects. Okay, so the outline of my talk is just trying to answer simple questions. And what can you learn from collision experiment on rare gas dimers? These dimers are not yet molecules, but not anymore atoms. So that's an interesting situation. Then you can say, okay, this simulated molecule, could you learn something on ion molecule collisions that you could not learn from a covalent molecule? And finally, this is constituted by atoms. Could you learn something on the ion atom collisions? So if I reformulate these questions, you see here that for the dimer, could it be considered that two completely independent atoms? Concerning the molecules, do you have access to some things which might be hidden by the covalent nature of the bond? And finally, concerning the ion atom, does the proximity of another atom leads to other processes which would not happen in ion atom collision with a single atom? And just to stress on this last question, you should remember that rare gas dimers are the simplest system with one atom in a weak interaction with the chemical environment. Okay, ion dimer molecule collisions are usually seen as a two-step process, because with ions, the interaction with the molecule can be as fast as femto or attoseconds, and this in 30 years or more, just by choosing correctly the velocity of the projectile. So you have this cartoon who tells you that first the projectile removes electrons from the target, and then the system dissociates. You can see it in another way with another vocabulary. You could say that you have a transition, a Frank-Adler transition from the ground state of the neutral system, neutral dimer, to an excited state of the molecular ion, and from there it dissociates, giving rise to kinetic energy on the fragments, and the sum of this kinetic energy is what we call the kinetic energy release. So from the branching ratios between all the different fragmentation channels, or from the kinetic energy release, you can learn something about fragmentation dynamics. And from the orientation dependence of the cross sections, or from the scattering angle obtained from the transverse momentum, you can learn detailed information. You can get detailed information from the primary process. Okay, how we do that? So we used three kinds of projectiles with different charges from 3 plus to 20 plus. All those beams accelerated by 15 kilovolt potential. And this beam crosses the supersonic jet, which produces the dimers. And then the charge state is analyzed by just an electrostatic deflector, which separates the different charge states on a position-sensitive detector. And the fragments are projected by an electric field on the position-sensitive detector. That's the usual cold trims. And this is how look our system. The main point is that dealing with rare gas dimers, you have to deal with a very dilute target, which you have to sort among a lot of monomers. Okay, this is the cold trims from which from the time of flight you get the charge over mass ratio, and from the position of the impact of the fragments on the position sensitivity detector, you get the other momentum components. And if you plot the coincident time of flight, the time of flight of the first fragment detected versus the second one, you can easily separate all the different fragmentation channels. And this line here, which is due to the momentum conservation, tells you that you are dealing with dimers. So from the momenta of the particles, you can derive the kinetic energy release as well as the momentum or the molecule orientation. And from the momentum sum, you get the scattering angle. So what's the difference between molecules and dimers? So with molecules, because of the covalent bond, you have very short internuclear distances. For example, for nitrogen, the distance is only 2 atomic units, and the binding energy is as high as 10 electron volts. And what you would have seen from the previous works on low energy or high energy collisions with ions is that you have a strong preference to have the same charge on both fragments. And this is due to high electron mobility. And this has been presented in the first talk of this conference by Robert Moshammer. That's another slide that I have stolen, I told you, where they used XUV pump probe to test the multiple ionization of iodine, and they were interested in asymmetric fragmentation channels. And they changed the time between the pump and the probe, and they look how much of this fragmentation channel they could get. And this is what the result is that if the pump is too close to the probe, you have none of this fragmentation channel, because if you remove more electrons on one atom too early, then the other electrons, because of the electron mobility, they just change the center and then just try to get to the equal sharing of electrons. And you have to wait after a certain time before you can get it. And if you translate this time in terms of distances, that's what it is. You can have this 1 plus, 4 plus fragmentation channel until after the distance between the two atoms has doubled. So same conclusion as we already know, is that the electron transfer is faster than the fragmentation. So it's very difficult to have asymmetric fragmentation channels with covalent bonds. Okay, van der Waals dimers. Now they are very weakly bound. The binding energy is only 12 millielectron volts, and the distance between the two atoms is large. What happens? So you can look to the different branching ratios. We have a strong asymmetry, a strong contribution of asymmetric fragmentation channels. And for example, if you remove 4 electrons to the argon dimer, you have more than 2 times more the asymmetric channel, argon 3 plus, argon 1 plus, compared to the symmetric one. So you might say it's not a lot. But if you look to the nitrogen case, then you have only, the ratio is only 0.2 between the asymmetric to the symmetric channel. So that's one order of magnitude difference in the ratio of the asymmetric to symmetric when you compare nitrogen, a covalent molecule, to a dimer. So this is the answer. We have a large, with the rare gas dimers, you have a large contribution of asymmetric fragmentation channels. This has been published in 2010 because of the low electron mobility across the dimer. So now we do better, because we have also here an even charge of the dimer. Could we see some asymmetry in this charge sharing? And furthermore, does this asymmetry, could we learn something from this asymmetry? So this dication will break into one argon plus and one argon plus. And you have two ways of producing this dication. The first one is to remove one electron on each argon. So you go to this repulsive curve and you have what we call the Coulomb explosion. The other possibility is to remove two electrons from only one argon. And then, because of the polarization, you have an attracting potential curve. The molecule imploses. And then, after a certain time, when they are close enough, you have a process which is called radiative charge transfer, which brings you back to this curve. We have an electron exchange, an electron capture from this one to this one. And then, since this happens at a closer distance, you have a larger kinetic energy release. And this, you see it directly on the kinetic energy release, where you have the Coulomb explosion peak and the radiative charge transfer. So now, you can separate these two processes. So you can separate the case where you capture one electron on both sides, and the case where you capture two electrons on one side and none on the other. So the conclusion is, yes, with these simulated molecules, we learn something. Now, because of this low electron mobility, which is a kind of memory effect, you can say where the electrons have been captured, on which center of the molecule the electrons have been captured. And in a molecule, you will lose this because of the rearrangement of the electrons on the molecule. So we can measure. Now, for this dication, we know the proportion of the asymmetric to the symmetric fragmentation channel. Okay, now let's say, can we treat the dimer as two atoms? So how to do that? We have to rely on calculation. So we made a calculation in an ion atom calculation. So since we are at low energy, we can safely use the other barrier model. Maybe I don't know if I go into the detail, but this is a model which works fine at those energy in ion atom collisions, where you have the projectile which approaches to the target, and doing so, you have the barrier which is lowered. Then electrons are molecularized between the projectile and the target. And when the projectile leaves, the potential barrier is raised again, and some electrons can be captured by the projectile or stay on the target. So we did this kind of calculation, adding a Monte Carlo part to the calculation just to determine randomly the orientation of the dimer and the impact parameter vector, and to calculate the transverse momentum exchange due to Coulomb repulsion. But each atom has been treated as an atom. There is nothing molecular in the calculation. And this is what we got for the branching ratio, and the agreement is quite nice, even for the asymmetric to symmetric branching ratio. We are fairly good agreement. But can we test it better? So we tried to see if we could get something from the angle. So our idea was very simple. If you have the dimer like this, and you have the angle, the projectile which is scattered on the right, let's say on the right, that would mean that it has been closer to this center compared to the other one. And if the projectile is scattered in the other direction, that would be the opposite. That's the idea we had in our mind. So just that you can understand what is plotted here, we have the dimer is along the horizontal axis here with the most charged fragment on the right side. And then we just plot the scattering angle of the projectile with regard to this distance. And we assume we have chosen dimers which are aligned perpendicular to the projectile direction. And for the symmetric fragmentation channels, what we see is that we have a symmetric shape with a preferential scattering transverse to the dimer. For the asymmetric fragmentation channel, we do see an asymmetry left-right, and this is the sign that the projectiles are more scattered on the side of the most charged fragment rather than on the side on the lowest charged fragment. And if you compare to the calculation, which is the red line, the agreement is surprisingly good, even for the asymmetric one with a small disagreement for this channel. But for the other fragmentation channel, the agreement is fairly good. And with the calculation now, we can tell, we have the agreement on the orientation, we can tell what was the impact parameter, because we have it in the calculation. And then you can plot these P of B 2D maps. Here, for example, to produce a pair of argon plus, the projectile has to pass at the equal distance of the two atoms. If it goes more closer to one, then you might have either double capture on one side and nothing on the other, or maybe another asymmetry. So this is signs the fact that the capture or the projectile captures on the closest atom it encounters on his trajectory, and this has been published very recently. So the second conclusion is this one. Yes, we could consider the two atoms are as independent in the dimer, because first the Monte Carlo, the atomic model works quite fine, and also we have a better access to the primary process because we can define on which center the electrons have been captured during the collision, and this was not possible to tell in a molecule, because you capture on one center, then the electrons rearrange, and then it dissociate, and you lost that information. And finally, does the proximity of another atom changes things, or gives rise to a new relaxation process? The answer is yes. If you ionize an atom or a molecule in a medium, now we know that because of this process, the surrounding atoms will try to decrease the charge and share the electron, missing electrons. They will share them on several atoms. Is it the only one? You know, of course, you know already the answer. This is this famous ICD, where if you capture an inner electron in a neon atom, for example, in a dimer, you might have an Auger effect across the dimer, meaning that one electron of the other atom will leave, while the 2s hole is filled in the next atom. So it has first observed in photoionization by these people, and it even gave Till Janke received the UPAP prize for his work on this ICD. More recently, it has been seen in fast ion impact collisions, and this is understandable because in both cases you understand that you can produce 2s holes in atoms. And one nice result that has been obtained in these studies is that the ICD can be a very important process to produce low energy electrons. And for example, here with the helium at the 0.6 MeV energy collision, you could have 14 times more low energy electrons compared to the simple atom, and due to the ICD. And this has also been observed at higher energy with heavy ions. So our question was, can it happen in low energy collisions? Because you have, in low energy collisions, usually you capture valence electrons more easily. Now, if you want to see ICD, you have to capture a 2s electron. Okay, that can be done, but without capturing any of the 2p electrons of the neon. So That's what we wanted to try to do. That's what I was saying here. So again, I don't know if I will come into this, but again, the kinetic energy release spectra will help you to sort among the three processes that you have to deal with, which are the Coulomb explosion, capture of one electron on each side, the RCT, which is capture of two electrons on one side, and then electron transfer between the two atoms, and then the ICD, which is a 2s hole and then an Auger effect, which needs the two atoms to play a role. So we did this with all our projectiles, xenon 20 plus, argon 9 plus, and oxygen 3 plus. I will not go too much into the details, otherwise I will be short in time. But the thing is that you cannot see ICD with highly charged ions. You could see ICD only in the case of oxygen 3 plus here, this peak, which is a little bit shifted compared to the Coulomb explosion peak. And for these projectiles, ICD dominates over the projectile Auger electron emission. So again, at low energy, ICD is still the main process to produce low energy electrons, free electrons. So if you compare these results to the calculation that we had, qualitatively the agreement is okay. And as you can see, you capture when you have a high charge state, the easiest is to capture electrons from both sides. That's the Coulomb explosion. But as the charge state decreases, the impact parameter or the cross-section need to be closer to the target because the charge decreases, and then the RCT starts to play an important role. And when the cross-section is really small, then you have to be very close to the atom of the dimer if you want to capture, and then you start to have even ICD. So we were interested to see if this continues if you still decrease the charge state. So now we have no experimental experiment, we just run the code, and what you see is this. As you have 5 plus, 4 plus, 3 plus, 2 plus, and when you go to 2 plus, ICD is still increasing. So what you should remember is that surprisingly, even if you think it's difficult to capture a 2s without capturing any other electron, it's possible that to have this process, you need really to go to low charge states, which have very small cross-sections well, the capture radius is very small, so you can do that. And now we know that even at low energy, low charge state, which is the case for ions at the end of their range when they slow down in matter, before they stop in matter, they have a low energy and they have a low charge state. So there's no ionization process for you to produce electrons, which might damage the surrounding matter. But this ICD process is there, important, and might play a role for this production at the end of the range of ions in matter. So this was my outline reorganized. Did we answer to the questions? Let's say, what did we learn on rare gas dimers? Well, we could say that assuming the two independent atoms is a fairly good approximation because of the agreement with the atomic model. What do we learn on ion molecule collisions? Now we know where the electrons are captured, even if the electron rearrangement in covalent molecules do not allow you to measure it. These simulated molecules allows you to find out, and the electrons are captured from the atom which is the closest to the projectile during the collision. And finally, what do we learn on ion atom collisions? Well, the proximity of the other atom opens new processes. First, the RCT, which shares the charge to the neighbors. The ICD, which is a new source of low energy electrons, even at low energy collisions, so at the stopping point of ion in matter. So it might play a role in radiation damage in matter and tissues. So if you just remember only one thing from this talk. Maybe this one could be a good one. Remember that these dimers are really the simplest system with one atom that you can hit with another ion or a laser, whatever, with a chemical environment. One atom being the target and the other one being the chemical environment, as they are acting as two independent atoms. So I would like just to give the names of all my colleagues who participate to this adventure, and I would like to tell you that Wael Iskandar, who is in the room, is the student who did all this work. Thank you for your attention.